Welcome everyone. In this video lecture, we will solve a problem on MOSFETs. So the question is, if the NMOS device has transconductance parameter mu n COX 100 microampere per voltage square, channel width 10 micrometer, channel length 1 micrometer, gate voltage 1.5 volt, source voltage 0, means source is grounded, and threshold voltage 0 0.7 volt. So we have to find the drain current in each of the three cases. For the drain voltage 0 0.5 volt, for the drain voltage 0.9 volt, and drain voltage for drain voltage 3 volt. So this one is the question, and this question is very similar to the last problem, and it is from the microelectronics circuit books. So in the last problem, we have calculated, or we have observed the mode of operation. So once again, we have to do the same thing for the calculation of drain current. First, we have to identify in which region the circuit, means the NMOS, is operating. So this one is our gate in, drain in, and this one is our source in. Okay, so for different VD, for 0.5 volt, we have to find the value of ID. Okay, for different VD, means 0.9 volt, we have to find the drain current ID. Okay, and for different VD, means 3 volt, we have to find the value of ID. Okay, so this ID we have to find. In addition to that, the given things are mu n cox, that is our transconductance parameter. So better we have to write everything. Microampere per volt square, the width 10 micrometer, L 1 micrometer. So W by L, simply we can say 10. Okay, get value Vg is 1.5 volt. Okay, so this Vg is 1.5 volt, Vs is 0 volt, and threshold voltage is 0.7 volt. Okay, so here this Vs is grounded. Okay, this Vg is, this voltage is 1.5 volt. Okay, just okay, so these are the parameters which is given, so we have to find. Okay, so for the very first case, say VD 0.5 volt, we have to find. So first of all, before we have to move ahead, I am just drawing the graph between ID and VDS, because this one is very important graph. So every time I am just plotting this graph for this one, for the NMOS. Okay, and this point is our VGS minus VT, and above this point, this one is in the saturation region. Okay, and this side is in the linear region, we can say linear region. Okay, so for the saturation region, once again I am writing the condition when VDS, this VDS value is greater than equals to VGS minus VT. So it is in the saturation region, and when VDS is less than VGS minus VT, it is in the linear region. Okay, so this one is very important, so every time I am just mentioning these two. Okay, so now we have to first find out the VDS. Okay, and VGS minus VT, then we have to compare, then after we have to write the trend current equation. So in this case, VDS, that is our VD minus VS. So VD is 0.5 volt and VS is 0. So simply our VDS will be 0.5 volt. And VGS minus VT, that is our VG minus VS minus VT. Okay, so VG is 1.5 volt. Okay, so we can directly write 0, VS is 0 minus 0.7. It should be 0.8 volt. So VGS minus VT value will be 0.8 volts. So this one is very important um, result. Okay, VDS and VGS minus VT. So now we have to identify in which region it will work. Okay, so first here we can easily say the VGS minus VT will be greater than this one. Okay, so I am just writing here. So here, okay, we have to select pencil first. So here this VDS is 0.5. So VDS is less than VGS minus VT in this case because this VDS value is 0.5 and this one is 0.8. So this 0.8 is obviously greater than this one. So this one is basically the device is in the it is in the linear region, not saturation. It is come under this no? So sorry once again. This one is in the linear region or we can say the triode region. Okay, so this one is a linear region or triode region. So now we have to write the drain current ID value in the linear region. Okay, so the drain current formula will be simply mu n cox w by L. In bracket we have to write VGS minus VT into VDS minus this formula we have to remember. It is very important formula in analog. So you have to remember this one in ID value in the ID drain current in the linear region. So mu and Cox value is given 100 microampere. So I am just writing microampere and the W by L. W is 10 by L 1 microampere. It should be simply our 10. VGS minus VT already calculated. So here 0.8. Okay, this one is 8. 0.8. Okay, once again 0.8 VGS minus VT into VDS is 0.5. So write it minus 0.5 whole square. Okay. So now if we solve this one, we can write it 10 to the power minus 3000. Okay, 10 to the minus 3. Then 0.8 into 0.5. So we can write it 40 by 100 also we can write. Means if we remove these two decimal, it 2 means 100 will become. And if we remove these two decimal, it will come 100. Okay, so one can write 25 by 200. You can directly use calculator also. I am doing like this. So 10 to the power minus 3. Then it should be 0.4. Then 12.5 means we can write like this 12.5. Then 0.125. So it should be simply our, here I am writing, means 0.4 minus 0.125. So it will come 0.275 into 10 to the power minus 3. Okay, so here I am writing, or we can write it 275 by 1000 if we remove this decimal into 10 to the power minus 3. Why we are writing? To write it in the micro ampere. So it should be minus 6. So it should be 275 micro ampere. So the ID value in this case will be 275 micro ampere. So this one is the, okay, 275 microampere will be the answer. Okay, for the particular value of VD, for in this case the VD value will be for how much VD value we have taken is 0.5 volt. Okay, for 0.5 volt the ID value will be 275 microampere. Okay, so for it in this case it should be 275 microampere and the device is in the linear region. linear region. Okay, this device will be in the linear region. So and it should be 275 microampere for VD 0.5 volt. Now next for VD 0.9 volt we have to find. Okay, so once again we have to write for VD 0.9 volt. Okay, so VDS will be simply our VD minus VS. First we have to find in which region this one is operating. So before that we have to find VDS, and VGS minus VT we have already calculated 0.8 volts, so no need to calculate every time VGS matter because gate voltage is constant and source is grounded. VT is 0.7, so 0.8. Okay, so in this case the VDS value 0.9 is greater than VGS minus VT, so it is in the saturation region. Okay, so in this case it is in the saturation region. Okay, so for VD 0.9 volt saturation region. So in this case we have to write the drain current equation ID in the saturation. So we have to very careful about the equation writing. 1 by 2 mu n cox W by L VGS minus VT whole square. This one is the exact formula. So now one can write 1 by 2 mu n cox transconductance parameter 100 into 10 to the power minus 6 into W by L is also 10. Okay, already 10 micrometer by 1 micrometer, and VGS minus VT already calculated 0.8, so 0.8 into 0.8 square, so we can write like this. So now again 1 by 2 into 10 to the power minus 3 one can write, and if you remove these two decimal it should be 100, so it should be 64 by 100, then it should be 32. Okay, 8 into 864, so 32 into 10 to the power minus 3. Okay, so or one can write it 32 into 10 to the power minus 5. So if we have to make it microampere, so what we have to do, we have to just multiply with 10 and divide with 10 with 10 to the power minus 5. So this 320, so one can write it 320, and if this go up, so it should be 10 to the power minus 6, so 320 microampere. So here the ID value, for this value ID value will be 320 microampere when the VD is 0.9 volt and it is in the saturation region. So we have already find, in this case it is in the saturation region for VD 0.9 volt, and the current will be 320 microampere. So I am writing that it should be 320 microampere, and the device in this case is in the saturation region. Okay, 320 microampere. So now for VD equals to 3 volt we have to find. So we did 3 volt. Again we have to identify in which operation, in which region this device is working. So VD minus VS, 3 minus 0, 3 volt. Okay, and VGS minus VT will be simply 0.8 volt. So here once again VDS is greater than VGS minus VT. Very simple. So it is again in the saturation region. Okay, so it is in the saturation region. Okay, for VD 3 volt. So now if it is in the saturation region, again we have to write the equation for the drain current in saturation region. Very same equation we have to write, and we have to do the calculation everything. So if we do the same calculation, it will come 320 microampere. Okay, so we can say it is somehow 320 microampere then. So it should be 320 microampere, and device is in the saturation region. Okay, Clear? Means our this value will be around 0 0.8 volt. Okay, and for the 0 0.9 volt, so in between, suppose here I am for the timing 0 0.9 volt, and like here it is 3 volt, so this one will be almost constant, so it should be 320 microampere, and in between 0 0.5, so here 0 0.5, this value what we are getting is around 275 microampere. 275 microampere. So this is all about this question. So the thing is that we have to very careful about the mode of operation. Okay, and the value of drain current we have to write very carefully. In saturation region, linear region, and mode of operation can be calculated, observed through this equation by in a NMOS. This one is basically for the NMOS. So this one is also important, and this graph, high pass filter type of graph will be there for RD and VDA. So this is all about this question. So thank you for watching this video.